Alright, hey, what's up guys? This is Bob. We're now called AlgoLock and we're going through top interview questions, medium set. We're done erasing strings and linked lists and we're down to binary trees and we're on question number 1, which is binary tree Inorder Traversal. So given the root of a binary tree, return the Inorder Traversal of its node's values. So you might be wondering what's the Inorder Traversal? They usually let you Google it in the interview. So this is the algorithm for Inorder Traversal. Traverse the left subtree, visit the root, and then traverse the right subtree. And if you look at these examples, it doesn't really tell you much. These aren't the best examples. So I'm going to give you guys my own example right over here. Let me just clear that up. So we want to traverse the left subtree. So we traverse BDE. Then you want to traverse the left again, and you traverse D. Then you want to visit the node, which is B. D, B. Then you want to visit the right, which is E. Then you want to visit the root, which is the root of this left subtree is A. Then visit the right, CFG. You want to visit the left, F, C, and then G. So F, root, and the right. All right, so that's cool. How would we do it if it was changed like this? So you might be wondering, all right, let's just run through the whole process again, the same algorithm. First the left, then keep on going left, left, D, root, which is B. Then you traverse to the right. So you're at E and you want to traverse the left first, just as you did in A. So you want to have I first, which is the left, E. Then you want to traverse the right and call Inorder on that. Traverse the left, call Inorder, traverse the right, call Inorder, and just visit the node. So traverse the right, you see JK, you want to do K first, and then J. So K, which is left, visit the node. Then go on to the rest of the tree. So that's the basic idea. That's a good example a really thorough example to go through the problem. So now let's actually see how would we solve this problem. So if you look at the algorithm they gave us, you see they call Inorder on the left and right. And what do we know about that? That's recursion. And honestly, that's the easiest solution you could find. It's probably the most trivial solution that you should find for any interview with binary trees, recursion, and then make an iterative solution. So that's what we're going to do next. Called recur in order. And let's define our return array. So list of integer. Return R is equal to new. Great. Then you want to recall this with the list of integer because we're going to be passing it through and adding all our values that we need to. Recur in order, root and return R. And over here, just return your return R. And over here, you want to check if the root is not equal to null. Because if the root is equal to null, we can't really add any values of it, right? Recur in order, root and return R. Okay, I'm just writing this out to make my life a little bit easier. So first we want to recurse on the left, recurse on the right, and in the middle you want to add the value. So return r.add root.val. At the end of this we can just return our return r, and we're Gucci. We're good. Taking a second, wait for me. Let's see. Compile error. Oh, we didn't add our name here. There we go. That should be good. All right, great. It's accepted. But what they do tell us in this follow-up is recursive solution is trivial. Can you do it iteratively? And that's a growing trend with these problems. It's a recursive solution that's really easy, and they want iterative solution. So this is O(n) space, O(n) time for a recursive solution. Now let's think about how to do this iteratively. We want to visit the left values, then the node values, then the right values. So if we add A, B, and D, and go through D, we see that B is the root value of D, and whatever subtree it is. So let's go through all these left values first. So we want to add A, B, and then D. And we'll worry about the right in a second. So let's make our current node equal to A. And you want to add A to the stack, right? Oh, I gave it away, but yeah, you want to add it to the stack. Why? Because you're going to A, B, D. and you want to access D first. You want to add D into the return array first. So last in, first out, that's a stack. So you want to add stack of values. Initially, they're just the left value. So there's A, D, and B. And eventually current node is equal to null. Then you want to pop these values. So you want to pop D and set the current node equal to the right of D. So that's how we're going to handle these right subtrees. Because, well, when we go through these right subtrees, we just want to do the same process that we did with our root node. So we're going to set the current node equal to the right value. And then while the current node is not equal to the right, we add all of its left children, and so on and so forth. And that way we do it in order traversal. So let's just run through a quick little example. So our return array, this is our stack, and this is our current node. So current node is equal to A. And in our stack, we want to add A, then B, because we keep on updating it to the left, then D. Excuse me. And eventually, this is equal to D.left, which is equal to null. Okay, great. Then our return array, you want to pop off D and set current node equal to the right of D. Because what if D had some right children? We want to handle that as well. So we pop off D. So it's no longer in the stack, and there's no right of D is still equal to null. So we don't add any of its left children because null is the end. Then we pop off B, and we wanna update the current node to the right of B to handle its right children. So we update current node to E. So while current node is not equal to null, you wanna add all the left children. So you add E and then I, and then eventually this is equal to null. I.left is equal to null. Then you want to pop I, E, then you pop I, set equal to I.right, which is equal to null. Then you pop E, set it equal to E.right, which is actually equal to J. Then you want to go through to J and add all the left children. So basically, that's the whole idea. This stack is storing all of this left path of each of these nodes. It's storing the left path of each of these nodes, and we update the current node equal to the right to go through the right as well. So we update add J and add K. So then we pop in K, J, K dot right is equal to null, J dot right is equal to null. And then we pop out A, the stack is empty, and our current node is equal to A dot right, which is equal to C. Then you pop in C, F, current node is equal to null. Then F, C, because F dot right is equal to null, C dot right is equal to G. And then we add in G. G has no left children, but if it did, it would be added in. Then you pop out G, and you're done. That's the original return array that we wanted. So this whole idea between the stack and current node is our current node. You go through our current node to add all the left descendants, and then we update our current node to right to keep on adding those descendants and going through it in order with the last in first out using a stack. So with that said, let's start coding up that solution. It's O of n time and O of n space because you're going through all of the n elements, and the worst case is just one long line in a stack, and that'd be O of n. So I could just show you guys if you want. Worst case would be something like this. Keep on the left, and you have to store all three values, right? All right, so with that said, let's code up the solution. Stack of tree nodes. Tree stack. New stack. All right, and we want a tree node, which is our current node, equal to root. So while our current node is not equal to null, or our stack is not empty, then what do we want to do? First, we want to go through and add all the left descendants of the current node. So while current node is not equal to null, tree stack dot push current node, and update the current node to current node dot left. cool. Then what we want to do is pop out the leftmost value of our descendants, which is tree kernode. So you go tree stack.pop. That's the leftmost child. You want to add it to our array. Return our .add kernode, and then what do we want to do? We want to update the kernode equal to kernode.write. So let me restore the tree that we had before. You want to update D, then you go to B, then you want to set to right, and you're basically running in-order traversal on the right by setting equal to kernode, because you had F and I, right? But you pop out I, pop out F, set it to the right. Pop out K, pop out J, then you go back and you go through A, C, G, I. That's the whole idea. This stack is storing the left descendants. This current node is used to handle everything else, so the root and all the right children. Alright, cool. I think that's good. Let me just check for any mistakes. Nope. Add kernode file. Alright, that was a mistake right there. You want to add the value, not the actual node. This is a node of, list of images. That's our return value. Oh, great, it worked. Now let's do a more comprehensive test. Oh, shoot. Yeah, that's accepted. I don't know if you guys can see that. It's down there. So, guys, thank you so much for watching. I'll see you guys in the next video. Like, comment, subscribe. Tell me what I can do to make these videos better. And thanks so much for watching.